Right now, as you are watching this, water temperatures across a 2,000-mile stretch of the Atlantic Ocean are running warmer than at any point since researchers began keeping consistent satellite records in 1981. The main development region, the strip of ocean between West Africa and the Caribbean where the majority of major hurricanes are born, just recorded an August sea surface temperature reading that peer-reviewed monitoring places roughly 1.5 degrees above the 20th century average. NOAA's Climate Prediction Center confirmed this month that the Atlantic has shifted into a phase scientists have tracked for over a century, and multiple long-term ocean buoys from the Gulf of Mexico to the coast of West Africa recorded the same pattern within the same 8-week window. This is not normal seasonal noise. Something significant is happening across the entire basin simultaneously. Today, we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally experienced a hurricane? Tell me where you were and what it felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. The pattern researchers are talking about is called the Atlantic Multidecadal Oscillation, or AMO, a natural cycle of alternating warm and cool sea surface temperature phases across the North Atlantic that repeats roughly every 20 to 40 years. It has been documented in instrumental temperature records back to the late 1800s and reconstructed even further using coral and sediment data. The cycle is not a theory on the fringes of climate science. It is one of the more well-established natural ocean oscillations, and it has a direct, measurable relationship with one of the most consequential numbers in American life. How many major hurricanes form in a given season and how strong they get before landfall. To put that relationship in context, researchers who study Atlantic hurricane activity have found that warm AMO phases correlate with roughly double the number of major hurricanes, meaning Category 3 or higher, compared to cool AMO phases. The last confirmed cool phase ran from the mid-1990s through the early 2020s in some analyses, though researchers have debated the exact transition point for years, since the AMO signal is difficult to fully separate from the broader warming trend caused by rising greenhouse gas concentrations. What has changed this year, according to the latest NOAA and Woods Hole Oceanographic Institution analysis, is that the signal has become unambiguous. Multiple independent lines of evidence, sea surface temperature, subsurface ocean heat content down to 700 meters, and shifts in the West African monsoon pattern that historically tracks with AMO phase are now all pointing the same direction at the same time. Here is why that distinction matters so much. A warm AMO phase does not cause any single storm. What it does is change the background conditions an entire hurricane season develops within. Warmer ocean water provides more energy for storms to intensify, reduced wind shear across the tropical Atlantic during warm phases allows storms to organize more efficiently, and a wetter West African monsoon feeds more of the tropical waves that eventually become hurricanes as they cross the Atlantic. Scientists generally do not conclude that any specific storm can be attributed directly to the AMO. What they can say, with a much higher degree of confidence, is that the statistical odds of an active, damaging season shift substantially once the basin enters a confirmed warm phase. Let's talk about what the last confirmed warm AMO phase actually looked like, because the historical record here is the backbone of the current concern. The Atlantic entered its previous confirmed warm phase around 1995 and remained in it through the mid-2000s. That period included some of the most destructive hurricane seasons in modern American history. The 2005 season alone produced Hurricane Katrina, which killed an estimated 1,800 people and caused over $125 billion in damage, along with Hurricane Rita and Hurricane Wilma in the same year. A season so active the National Hurricane Center exhausted the standard alphabet naming list for the first time on record. That same warm phase also produced Hurricane Andrew in 1992, which at the time was the costliest hurricane in U.S. history, and a string of major Gulf Coast and Atlantic seaboard landfalls that reshaped building codes and insurance markets across multiple states. To put a number on what researchers are now projecting, NOAA's updated seasonal outlook, revised specifically in light of the confirmed AMO shift, has raised its estimate for above-normal hurricane activity to a range researchers describe as significantly elevated compared to the cooler phase baseline used in outlooks from just a few years earlier. That is not a prediction that this specific season will produce a Katrina-scale event. There is currently no scientific evidence allowing forecasters to predict a specific storm's track or intensity months in advance. What the AMO shift does is raise the statistical floor for the entire 6-month season, more storms reaching major hurricane strength, and a modestly higher chance that any individual storm intensifies rapidly before landfall. The kind of last-minute strengthening that has become one of the most dangerous and least predictable aspects of recent hurricane seasons. If you follow ocean and climate news at all, the phrase AMOC collapse probably already rings a bell. And it's worth addressing directly because it gets confused with the AMO constantly online despite being a completely different phenomenon. The AMOC, the Atlantic Meridional Overturning Circulation, is the deep ocean current system that moves warm water northward near the surface and cold water southward at depth, the same system dramatized in disaster films as shutting down and freezing Europe overnight. The AMOC is a slow, deep circulation pattern studied on timescales of centuries. The AMO is a surface temperature oscillation studied on timescales of decades. Some researchers believe the two systems may be connected, since a weakening AMOC could theoretically influence surface temperature patterns, but that link remains an active and unsettled area of research, not a confirmed mechanism. Scientists cannot currently confirm a full AMOC collapse is underway, and the confirmed warm phase headline behind this story specifically concerns the AMO, the surface pattern already directly tied to hurricane risk, not the deep circulation system. Let's talk about the coastline itself, because that is where this pattern actually translates into risk for people. NOAA's sea level rise technical report places the east and Gulf Coast at an average of roughly 1 foot of relative sea level rise by mid-century, driven by both warming ocean expansion and land subsidence in specific low-lying areas like southern Louisiana. That baseline sea level rise means storm surge, historically the deadliest single element of a hurricane, now reaches farther inland and higher onto structures than it did during the last confirmed warm AMO phase in the 1990s and 2000s, even for a storm of identical wind speed and pressure. That changed fast in terms of practical flood risk, because it means coastal defenses and evacuation zone maps drawn using older storm surge modeling may now understate the actual water reach for a comparable storm today. Here is the other piece researchers are watching closely: ocean heat content at depth. Surface temperature alone does not tell the whole story of a storm's fuel supply, because a hurricane passing over water that is warm only at the surface can churn up cooler water from below, a natural braking mechanism that has weakened some storms in the past. This year's subsurface heat content readings down to 70 meters across the main development region are running well above the 20th century average, meaning that natural braking effect is measurably reduced across large sections of the basin, one of the specific factors behind this year's revised, more concerning seasonal outlook. Keep an eye on the West African monsoon, too, because that is the often overlooked upstream piece of this entire system. The majority of the strongest Atlantic hurricanes begin as tropical waves rolling off the West African coast, and monsoon strength directly influences how many of those waves form and how much moisture and instability they carry with them across the ocean. This year's monsoon season has tracked notably active, consistent with the historical pattern researchers associate with AMO warm phases, adding another independent line of evidence to the broader confirmation. The difference between a coastal community that weathers an active season with minimal loss of life and one that does not is not luck. It is preparation, updated evacuation planning, and how seriously storm surge modeling has been taken in the years beforehand. Florida, Louisiana, and Texas have each invested substantially in updated levee systems, elevated infrastructure, and improved early warning capability since the 2005 season exposed catastrophic gaps in coastal preparedness. The National Hurricane Center's forecast cone and rapid intensification alerts have both improved measurably in accuracy over the past 2 decades, giving coastal residents more reliable lead time than existed during the last comparable warm phase, even as the underlying ocean conditions themselves have become more conducive to dangerous storms. So what happens next? NOAA and independent research institutions will continue monitoring sea surface and subsurface ocean temperatures throughout the remainder of this hurricane season, updating seasonal outlooks as new data comes in rather than treating this month's confirmation as a final word. Despite dramatic online headlines characterizing this as an unprecedented planetary emergency, there is currently no scientific evidence that this specific AMO shift is outside the range of natural variability documented over the past century, and researchers have been clear that this is a confirmed natural cycle interacting with, not separate from, the longer-term warming trend rather than a standalone catastrophe. Let's go deeper on how researchers actually confirm an AMO phase shift, because confirmed is a specific technical claim, not a loose descriptor. The AMO index is calculated from detrended North Atlantic sea surface temperature anomalies, meaning the long-term greenhouse warming signal is mathematically removed first, isolating the oscillation itself from the broader warming trend layered on top of it. Researchers require the index to remain consistently positive across a rolling multi-year window, not just a single warm month or season, before formally classifying a phase shift. NOAA's confirmation this year was based on the index holding a sustained positive reading across the preceding 31 months, combined with corroborating subsurface and monsoon data, which is why the announcement carried the weight it did rather than being treated as routine seasonal variation. It's worth understanding why the distinction between AMO and the broader warming trend actually matters for people trying to make sense of their own risk. A warm AMO phase riding on top of decades of independent ocean warming from rising greenhouse gas concentrations is a different, and by most research assessments more concerning, situation than either factor alone. Some of the ocean heat content readings driving this year's revised seasonal outlook reflect both signals stacked together, which is part of why several research teams have specifically avoided directly comparing this year's numbers to the 1995 warm phase transition on a one-to-one basis, even while the historical 1995 to mid-2000s period remains the most useful reference, point available for understanding how a warm AMO phase translates into real hurricane seasons. Now let's talk about which coastlines carry the most exposure specifically, since that is ultimately the public safety question underneath all of this. The Gulf Coast, from the Texas coastline through the Florida Panhandle, sits closest to the warmest waters in the main development region's extension into the Gulf of Mexico, and historically has absorbed a disproportionate share of major hurricane landfalls during prior warm AMO phases, including Katrina, Rita, and Michael. The southeast Atlantic coast, from Florida through the Carolinas, faces a different but equally serious risk profile. Storms that intensify rapidly just offshore with limited time for evacuation before landfall. The Northeast Corridor, while historically less frequently struck by major hurricanes, carries its own elevated concern specifically because of Superstorm Sandy in 2012, a reminder that warm phase conditions extending storm reach further north than typical forecasting assumptions is itself part of the pattern researchers are now watching for again. This is also a moment worth using as a genuine prompt rather than a scare. If you live anywhere along the Gulf or Atlantic coast, this is a reasonable point to check that your household actually has a real evacuation plan, that you know your specific flood zone designation, and that you have basic hurricane supplies ready well before a storm is bearing down. None of that requires panic. It requires the kind of preparation that matters most in the exact years a confirmed warm AMO phase makes it statistically more likely to be tested. We'll continue tracking this story as the season develops, and if NOAA issues an updated outlook based on new data, we will bring you the details as soon as they are confirmed, not before. Let us go. See you in the next one.